Kia ora Year 12 and 13. In this video I'm going to do question 1 from the foundation worksheet that I've given you to practice for the trig internal. So what we've got here are two curves, a blue function and a red function. And we have to find out three things. First we have to find the features of each graph, and that will help me find the equation for each graph. Next we have to figure out where each graph has a value of -1. We're going to do that in two ways. We're going to find the general solution, and we're going to find the particular solutions for the picture that we've got in front of us. Okay, so we'll get the general solutions first, and then we'll substitute in values. And you can see from looking here that on the blue curve there are going to be 6 particular solutions that I'm going to find, and you can mark them on now. And for the red curve, we're not going to have as many, we're just going to have 1, 2, 3, 4. Okay, but first let's have a look at what kind of function I should choose to make my life easiest for each one. So I'll take off this for now. I'm going to start by modelling the blue curve. Now the blue curve starts up here at the maximum, so if we choose a cosine graph for this, we're going to have a little bit less work. So we'll write this as y is equal to a cosine of b x plus c plus d. But we can start by seeing that we're starting at the maximum, so we've got no horizontal shift. That means that c is equal to 0. If instead I start with a sine curve, I'm going to have to figure out where the starting point of the sine curve is, and then shift everything along. It's definitely more work, especially when we go to solve the equation later on in the question. Okay, so take some time to make that decision sensibly at the start. The next thing that I always do is look at the vertical shift, and for that we need to find the midline. Now you can see it, but if you suddenly have your brain freeze over, let's just have a nice mechanical way to figure out the midline. Well, I've got my high point here of 2 and my low point of -6. So 2 plus -6 divided by 2 gives me -2. That means that my cosine graph has been shifted down 2 units. So d is equal to -2. So we can mark that in on here, and you can see that that's going through the middle of that graph. That makes it very easy to see the amplitude. So the amplitude goes from, well, 2 ways to think about this. You can just see it on here as that distance. The amplitude is 4. But the other way you can get it is by taking the maximum minus the minimum and dividing that by 2. Okay, so that's 4. And so A is that value. The last thing we have to work out is the frequency and the period. I think the easiest way to do this is to look at how many full cycles we've got within one normal period for a cosine curve. So here's 0 and here's 2 pi. How many full cycles does my blue curve do? Well, we start here and here's 1, 2, 3. So the frequency of that graph is 3. And that means that the period of the function is the normal one of 2 pi divided by 3. So b is equal to 3. So we're ready to write the equation, and it will be y is equal to 4 cos of 3x take away 2. Okay, so there we go, that's the first one done. And that's the harder of the two, I think. Let's look now at the red graph. So I'm going to clean all of this up and we'll start over. So the red graph has we've got a choice of sine or cosine, and this time I'm going to choose sine. And I'm doing that because here's my starting point for the curve, and it's following the standard sine pattern. So we're going to go with this function, y equals a sine b times x plus c plus d. And we can start out by saying again, no horizontal shift. So c is equal to 0. And the midline is at 0. So there's also no vertical shift. D is equal to 0. Whoops, better turn off ink to shape. D is equal to 0. Right, what have we got? Well, we've got the amplitude is not the usual 1, so the amplitude is 2. Right, amplitude is 2, and we also need to look at the frequency and the period. So we're getting the amplitude from here, the distance up to the top. So that tells me that A is going to equal 2. And lastly, the period of the function. Okay, so just got to be a bit more careful with this when we're doing a sine one. It's easier to muck it up. So here's one full cycle gets me to there, and then another one to here. So the frequency is 2. The period is the usual period for a sine curve divided by that frequency, which is pi. And so B is equal to 2. So my sine curve is going to be y equals 2 sine 2x. Now, right, so we've got the equations and we've got the features for the two of them. The next thing that I need to do is to figure out a general solution and then particular solutions for where each graph has a value of -1. Okay, so pause the video and have a go at doing that yourselves before you watch me do it. So we'll do the cosine curve first. So we're solving this. Add 2 to both sides. Now divide through by 4. The next thing I'm going to do is to find my alpha value, which is my principal solution. So the angle whose cosine is 1/4. So that's 1.3181. So what am I doing here? Well, I'm saying if I had my ordinary old cosine curve, not cosine of 3x, but cosine of x, what angle would give me a cosine of 0.25, and it would be out here, right at 1.381. But we don't really think about doing that once we've got used to doing general solutions, but that's what alpha is. So we take that alpha value and we chuck it into our general solutions formula. So 3x is going to equal 2n pi plus or minus 1.3181. Now I divide both sides through by 3 and I get x is equal to 2/3 of n pi plus or minus 0.4394. So that's my general solution, and I should write down that this is where at these x values the curve will cross the line y equals -1 or something like that. But now what I want to do is to find particular solutions between 0 and 2 pi. So when n equals 0, we get two values. We get x equals 0.4394, so that's one of my 6 values, or -0.4394. Right, so what I'm doing here is I'm substituting values of n into here. For n equals 1, so that one's not in the domain. For n equals 1, we get x equals 2/3 pi minus 0.4394, and x equals 2/3 of pi plus 0.4394, 1.655 and 2.533. So both of those are good. And remember, we've found out that we're looking for 6 of these, and we can check all of this on our graphics calculator. X is equal to 4/3 pi minus 0.4394, so that gives me 3.749, and the other one is x equals 4/3 pi plus that number, so that's 4.628. So we're up to 5, we just need to find one last value, and that's going to be the lower one when n equals 3. So we're up to 2 pi, so 6 pi on 3, minus 4.4394, which gives me 5.844. And the other one, which we'll reject, is this one here. So that's bigger than 2 pi. So there you go, we've got all 6 solutions. Let's just quickly hop to GeoGebra and see what it looks like. There we go. So you can see those 6 solutions sitting on there, and you can do this in your graphics calculator to check that your graph looks exactly like the one that you started out with. Now let's very quickly go and do the same thing for 2 sine of 2x. This is one where you can do it with exact values, so I'm going to do that. So we're solving 2 sine 2x equals negative 1, sine of 2x equals negative 1/2. Alpha is equal to the angle whose sine is negative 1/2. Now you don't have to do this with exact values, but if you're watching this from my 13 MCA class, you should be doing it like that. You need to be pretty comfortable with them. Remember, the definition of sine of x is the vertical component over the hypotenuse. So in here, we're looking at this angle here. This distance here, this point here is negative 1. The length of this line is 2. So alpha is equal to negative pi on 6. That gives me my general solution of 2x is equal to n pi plus negative 1 to the power of n times negative pi on 6. And we're not quite finished yet, we need to get that to x. So x is equal to n pi on 2. You can leave it like this, or you can write it as minus negative 1 to the n times pi on 12. Right? So that's your general solution, and you're going to write a sentence saying that these values will give us the places where the line meets y equals negative 1. And then you're going to pick out some values, and you're looking for 4. So if we put in n equals 0, we get x is equal to negative pi on 12, and that's not in our domain of 0 to 2 pi. N equals 1, we'll get x equals pi on 2 minus negative pi on 12, which is 7 pi on 12. N equals 2. Let's have a look. X is equal to pi, take away pi on 12, which is 11 pi on 12. So that's the first one. That's the second one. Remember, we're looking for 4. And n equals 3. I'll have x equals 3 pi on 2 minus negative pi on 12. That gives me 18 pi on 12 plus pi on 12, which is 19 pi on 12. So that's my third one. And the last one comes from n equals 4. X is equal to 4 pi on 2, or 2 pi, minus pi on 12, which gives me 23 pi on 12. Now it's fine to get those not as exact values. So if you're watching this and you're not confident with the special triangles, then that's okay. They are an important part of Trig though, and you really should have them. You're going to need them down pat for some of the other standards this year as well as Trig. For example, in harder differentiation problems and integration ones, they can crop up as well. Alright, so that's just one of those questions done very slowly. I'm going to do 2 more videos going through questions 2 and 3, which are similar. Thanks for watching.